All right. Thanks everybody for joining. This is our Robotics Community Group meeting, which is a presentation meeting today. Today's Wednesday, June 19th, and it's going to be at least like the last official community group meeting before summer break. So I'm going to start with a couple of announcements first, and then I'm going to give the word to Khalid, who's going to give a nice presentation for today, and then I will end up with a couple of conclusions. So the announcements is just kind of very similar to the announcements last of 2 weeks ago. So there's going to be the Robotics Developer Day on Friday, 5th of July. I'll be giving a skill learning session, as they call it, about for like 45 minutes, where I'm going to talk about ROS2 with a tiny quadcopter. Again, thanks again, Reese, for helping me out a little bit with the simulator. Let's see if I can indeed tune it in time. But it's this is the link right here. I will post that in the chat as well, if I can. Oh no, no teaser yet. One moment. I'll post all of those links later. Also, I would like to remind you guys that there's also connected to the Robotics Developer Day is also the ROS Awards. So let's vote for any aerial-based autonomy stacks or aerial vehicle developers or aerial robots. We have 2 little currently in there, so make sure let's select a couple of those. Let's look at the aero robotic landscape and whatever which one you like and add it to the list. And also, if Bitcraze is a sponsor of the Robotics Developer Day, so if you want to join that day, please contact me personally through this email, kimberly@bitcraze.io, or DM me on Discord for a discount code for the pass. I think the day itself is free to follow, but if you actually want to join and actually participate with the tutorial with a project, you do have to pay for a pass. But I have a discount code for you, so please contact me if you would like to join for real. And just to kind of give you a little bit of a teaser of what I'm going to show as well as tutorial. I'm also going to show the different simulation. It's a very tiny teaser. I will just show it to you again. Just a little free time mapping type of example that I will build up in that one tutorial. Very tiny teaser. More to be seen. All right, so I will give the floor to Khalid, who's going to talk about the new generation of flight controllers. So let me stop presenting. And
it's quite nice demo that you have shown here. It looks like an ultrasonic or a lidar that rotates with the drone. And
yeah, it's a TOF sensor, so it's not really a lidar, but you can make a lidar.
True,
but it's like the Grace Fly is a small thing. But yeah, thanks.
Sounds perfect. So let me share my screen, please. 1 second. Yes. So now can you see my screen?
Yeah.
So
perfect.
Welcome everyone. Thank you for the opportunity of having me. Today we will be talking a little bit about new generation flight controller. In this presentation, we will be presenting or introducing a very small concepts that we will just be revising with each other. For sure everyone knows about these small concepts of what are the control loops to get the drone flying from in an autonomous manner, and then we will go through some flight controller architectures for different generations or different variations. First, we will start with classical, and then classical plus, and then the new generation flight controllers. And then we will talk a little bit about our software stack, what do we do, and our software aerial platform. What do we do in it? What is the features that distinguish it from any new generation flight controller that is already available? And then we will show some demos. I hope they are quite nice, I hope. And then we will show the future work that we are expecting to do in the future. And then some question and answer. And finally, some common question and answer that we were rapidly asked when we talk to other people. And finally, the question and answer, which will be an open discussion for everyone to ask anything. So let's start. First of all, before we go through our software stack and our presentation, maybe a short introduction about myself. My name is Khalid Elmadawi. I'm a senior software engineer at Sigma, and I am the manager of the Egyptian branch of Sigma Embedded. I have a master's and a bachelor degree from Cairo University, Faculty of Engineering. I have something around 11 years of experience in various domains: artificial intelligence, automotive industry, autonomous driving, simulation, perception, and embedded systems development, and embedded system development over Linux. If I would say that the picture that you can see here in front of you is simply one of the things that I'm proud the most in my career. These are two images. One of them is coming from a real sensor, and the second is coming from a simulated. And this was one of the outcomes that I had done, or me and my team had done when we were working in the domain of simulation in a topic called real to sim and sim to real. I put this image up. I put this image here just to have a glimpse about the problems that I used to engage with through my career when I through my career in different stages. Before we talk a little bit about our software platform as well, maybe a short introduction about Sigma. What is Sigma? Sigma is one of the leading software consultancies. Sigma has something more than 66. Sigma has more than 5,000 headcounts in a global scale, in addition to 2,000 more in its network. Sigma is present in more than 66 sites in a global manner. Most of them in United States and in Europe, and few of them is outside of United States and Europe. And Sigma Egypt is one of the few sites outside of United States and Europe. That's a short introduction about what is Sigma. And now let's go to our presentation. So simply, for any drone system to be able to achieve a certain task, whatever it is required from it, for example, taking off, observing a certain state, and going back again to either the same place or another place, it requires one of two. It requires two main control levels. The first control layer is called the inner control layer. The second control layer is called the outer control layer. Of course, much more complex systems requires many different control levels, but that will help the drone to do a certain functionality that is required from it. But we are talking here about the bare minimum, about the flight controller or about a drone to achieve in order to achieve a task in an autonomous manner. The inner control layer simply it is responsible that the drone would the rate of rotation of the drone at a certain angle would equals to 0. So, for example, if we have a drone that is it's required from it just to hover, then the required angle that is required to not to rotate out of it is 0. So, if it is the rate of rotation at 0 angle at an angle that equals to 0, then the drone will keep in its place. If the drone wants to move forward, then the rate of rotation at a certain angle that is set to the inner control loops, the angle of rotation for this control loop should be equals to 0, and by that somehow it identifies how the drone behaves. The outer control loops simply it is for you can think of it as a simulated pilot, where simply it generates a set of commands and a set of angles where somehow it defines the behavior of the vehicle itself. For example, if you want to as we said, that if you want to move forward with a certain velocity or accelerate forward or backward, then you need to generate the set of angles that will help you to generate to move from point A to point B, accelerate, and then when you get close to point B, you decelerate, and then you hover again. This is a short brief about kind of the two levels of control, the minimal two levels of control loop that is required for the drone to do an autonomous task without crashing. And then the thing that is the board that is handles such inner and outer control loops is called the flight controller. The flight controller is the heart of the drone. It allows it helps the drone to achieve what is required from it through observing the vehicle states, make a state estimation on the observed and the non-observed states, and process the control loops and output a stabilized control signals to the motor, and finally communicate with the pilot or the ground station in order to achieve the mission that is required from it in a correct manner. If, for example, let's take the same example that we took in the last slide, and it will just propagate, this example will propagate with us through the next slides. If we want to go from point A to point B, then simply the microcontroller will require to observe the longitude and latitude of the drone from the GPS sensor. It requires to observe the rotation rates from the IMU. It requires to observe the heading from the compass. It requires to observe the pressure from the barometer, to estimate an altitude, and requires to observe the distance from the ultrasonic to observe the low range altitude. It requires to interface with the motor drivers to be able to control the motors. It requires to communicate with an RF module to be able to communicate with the other ground station or the pilot. Each module requires a subroutine in the microcontroller that interfaces with each module to observe a state or subroutine actually to do other processes. For example, we have the subroutines such as the sensor fusion, the control loops, and the navigation subroutines. These types of subroutines, they do not observe a certain state, but they are doing some processes that help the drone to do its mission in an autonomous manner and in a stable way. This software stack somehow is called combined, is called a flight controller software stack, or a firmware for a drone or a flight controller. And this is mainly the classical way of doing the flight controllers, or how classically a flight controller works actually. There is another approach that is still considered as a classical flight controller, but it is more safer and more redundant, where simply the subroutines are divided into a subsets of subroutines. So the state observation and the sensor fusion are being done on a single microcontroller. The RF communication is done over a second microcontroller. The navigation and the control loops stacks are done over a third microcontroller. And in such setup, it is a little bit safer. It is more immune from hanging, but it still has the limitations where it's still working with it's still working in megahertz, and it is still bounded with the processing and memory resources or limitations that are in the microcontroller. And then there is another approach, the third approach, which is the second approach, pardon me, which is the classical plus+, where simply, why won't we have a mission computer that helps the drone somehow to do much more complex processes and to be able to interface with more advanced sensors, for example, that requires some computationally cost processes or processing power to compute. So, for example, so simply in this setup, the periodic and the inner control loops are running over microcontrollers, where somehow it is closer to the motors and closer to the sensors to observe new states. And the kind of the more computationally costly processes are running over a mission computer, where simply they are running either in a single process and it is divided into different subroutines, or it is being processed in sequence, or it can be set up in multiple processes, and each process is somehow um, doing a certain task, and different processes are communicating within each other through a meta operating system, which is most probably it will be ROS or any other meta operating system. And the good thing about this setup is that it introduced a new area for the drone where it can operate in something called a GPS denied environment. And somehow it introduced a new aspects that the drone can be used. And then came a new perspective. Some other people came. Why won't we, if we are going to somehow, if we have already a setup where we have a flight computer and a flight controller, why won't we get all of the software stack from the flight controller and put all of it in the flight computer? And simply, this is the new generation flight controller, where simply in the new generation flight controller, each subroutine in the flight controller process that is or in the flight controller software stack will be an independent process that somehow communicate and shares its data through different inter-process communication protocols. By that, we will gain multiple benefits, such as, for example, extending the resources of our flight controller software stack, extending the resources that our software stack is running over it in processing power and in memory. In addition to software modularity and being able to extend our software stack as much as we wish to kind of to fit in different autonomy or in different environments. For example, let's take the same example that we took before. If we want to have an attitude hold, then simply GPS process will fetch the altitude, the longitude and latitude. IMU will fetch the rotations. Barometer will fetch the pressure, and from that we will take we will calculate the altitude. Compass head will calculate the heading, will fetch the heading will observe the heading. Ultrasonic will observe distance from the ground or for short range distances. And then all of these states will be shared with the sensor hub or sensor fusion, which will make an observation for the observed and non-observed, will make an estimation for the observed and non-observed states. Same for camera and LiDAR will take new frames, and then it will be shared with the localization and perception, its input will be shared with the navigation, so it can make a local and a global navigation planning for the mission that is required from it. And then it will share it with, or it will set the behavior to the control loops, which will go to the sensor fusion, and then it will try to see what are the actions or what are the control commands that is required to be sent to the motor drivers process that will be sent to the motor directly. And then the telemetry will be an independent process that somehow is sniffing or somehow reading from whatever state or observing whatever state from different processes, and then it will be shared with either the ground station or with the pilots. When it comes to modularity, as we said, or one of the advantages of this software stack is modularity, and scalability. You can scale it as much as you wish. So, for example, in the state estimation of the drone, you can actually scale it by maybe, for example, use the optical flow coming from the camera, and simply all what will be needed or required to be added is that the sensor fusion will just take the new states or add the state of the optical flow to the states that is required to be added in the fusion states or in the observed states. So it can make a new estimate, and by that it can make a more certain estimate, and by that it can actually withstand the same performance within within a variety of different inputs and variety of different environments, I would say. But it's still nothing is super nice by its own or forever. There is always challenges you need to consider when you encounter such setup. The challenges, one of the biggest challenges, not the only challenge, but one of the biggest challenges is how will you deal with the resource allocation actually for different processes. For example, we have the IMU, we have the barometer, we have the compass. These three sensors are three independent processes. Everyone is working in a periodic manner, and at the end of the day, the three sensors are interface might have the same physical interface. For example, the I2C peripheral, communication peripheral. Then how will you as a software engineer, or how will you be able to handle uh, different different processes fighting over the same peripheral? This is one of the problems that you need to somehow have a heads up over it when you are encountering such problem in the new generation flight controllers. But how did we solve it? Or how did we do our software stack? Let's discuss it in the next slides. Simply, what have we done? What have we done here? Simply, our software stack, we have done the new generation flight controller based on service-oriented architecture. But what is the service-oriented architecture? Simply, before we say what is service-oriented architecture, we have done a software stack based on service-oriented architecture for autonomous vehicles that ensure modularity and cybersecurity, software safety, better resource allocation, and increase the capacity, the processing capacity for other different processes. What do we have? We have divided our software stack into multiple layers. Each layer contains a set of services. Each service provides an interface, either an interface for a certain physical, an interface for either a physical, a peripheral, or a shared resource, or an interface for a process to be executed. If we will discuss the same example that we have discussed it in the previous slides, which is attitude hold. We want to hold our attitude. So simply, the attitude server will communicate with the control loop server, and it will set for it the set points, where somehow the attitude is a client for the control server. And in the control server is a client for the sensor hub server. Control loop server is an actual client for the sensor hub server, where it will ask it for the latest estimated values or the observed and non-observed estimated states. And the sensor hub will ask for the IMU server. It will go for it and ask for it. Sir, IMU, can you give me the latest observed states of rotation? And the IMU will go for the I2C server, and it will ask it for the latest reading from the physical sensor through kind of this communication peripheral or whatever. And by that, this cycle goes on and on it can go up for 1 kilohertz. as a kind of the periodic cycle that is of such requests are being done in a frequency that goes up to 1 kilohertz, and it can goes for much more than that. Um, this is somehow the in a briefly what is our software stack, and somehow um, let's discuss a little bit now what are the benefits or what are the added values of our software stack than the other software stacks that are already in the market. Than the other new generation software stacks that are already in the market. So let's start with, is there actually is there any software stacks that are new generation? The answer is yes. There is a new generation flight controllers that are already there in the market. They are based over publisher subscriber way of work, and somehow let's remark the differences between the publisher subscriber way of publishing data and the service oriented architecture. So first, if we have a process that is publishing a certain state, and you can and you are observing it from another state um, in your kind of software stack itself. If we have if there is an IPC, an intra-process communication, a process that has an access to the network itself. So the first question is, can it subscribe to the same message, and can it sniff this message? If the answer is yes, then you are having a case that requires to be covered in the cybersecurity for your software stack. If you have the same case, if you have an IPC or an RPC, a remote process communication or an inter-process communication, that is somehow publishing the same message over or a corrupted message with the same message format over your network somehow. So if and somehow it will affect the observer or the subscriber state. So if the answer is yes, then you are having a case that you're required to cover it in somehow to make sure that your process is not being somehow will not be affected by other processes that you do not want to subscribe to them. On the other hand, if we would look to the service-oriented architecture, you are simply having when a client make a request from a server, you are running an actual API in the server. So simply you can add a cybersecurity layer or a security layer where you are checking who is requesting this message. So it somehow it can block the other processes that you do not want them to observe this state or to make this request to process a certain process or to behave in a certain behavior. So this is the first case, or this is the first feature that somehow is a little bit different in the service-oriented than the other one. If you would look into another case where simply you are having multiple subscribers for the same message. So simply, if you are having different processes that are subscribing to the same message, and you are having this is working with a frequency 1, frequency 2, frequency 3. At the end of the day, you are not, I won't say that you are limited to publish with the max frequency, but it is recommended for you to publish with the maximum frequency. And by that, in this setup somehow, this is an overload or overhead for the subscriber processes. If we would take a small example, if you are having an application layer and a control loops, and both of them, for example, a process that processes the LiDAR sensor or LiDAR point cloud and trying to make a map out of it to match the point clouds together. And another process that somehow is somehow the control loops, which is using the rotation, a certain states, the certain rotation states, for example, that controls the rotation of the vehicle itself. So simply, the control loops works with 1,000 hertz, and the point cloud matching, it works with actually 10 hertz, or you will be lucky if it works with 2 hertz, something from 2 to 10 hertz as an onboard processing. So somehow you are forcing somehow the point cloud matcher process to subscribe to quite higher frequency that it doesn't need that. On the other hand, in the service-oriented architecture, you can work different processes, and they can subscribe, or they can ask from the server as different clients with different with different rates, or different frequencies, and it will just work out fine, and there will be no problem about that. So this is one of the second points that service-oriented architecture is having an advantage over the service publisher subscriber. And then one more feature is software safety. How is that? As we have discussed before, pardon me for this S, it should be down there. One of the things that we discussed before is one of the cases when we have multiple processes that are interfacing with a physical property or physical peripheral over the board itself, over the physical board, and these different processes are not communicating with each other about, or they are not syncing with each other, how to allocate and disallocate this resource. Somehow this might be considered as an unsafe practice somehow, and this is considered, and this is how we handled it. We simply, as we mentioned before, our software stack is is a set of layers. Each layer contains a set of process services. Each service is either controlling or managing the traffic of a certain resource, or managing the traffic of or doing a certain process. This is how we handled it. How will this reflect us in our behavior? Simply, if you want this to work with one kilohertz for the IMU rate, and you want a quite high as well magnetometer for heading measurement or heading observation, and barometer, you want to get the maximum barometer frequencies that you want to. If you want to have the maximum frequencies for the three, you can achieve it with this setup. But in this setup, one of the problems that will happen here is simply from the system level, that your observation will just, your observation frequency, it will just drop. So for example, if you are having the IMU by itself, it will work out fine with 1K with this setup. And then if you add more sensors to it, it will just, from the 1000K, it will drop to 800, and then it will drop to 100, and it will just keep. Why is that? This might be one of the reasons of it. It might be the conflict of fighting over different resources. That's briefly our software stack. Demo time. In this demo, we are simply demonstrating two cases for attitude hold. First case is it can counter disturbances. Second case is we give it a set point and we return it back. As you can see, and voila. Somehow in this demo, we are just holding it with two kind of what's called two wires for safety, no more, no less. And in this demo, it is an altitude hold, autonomous altitude hold. So we give it an altitude here from kind of a command here, and then it just hovers and takes kind of the altitude. The astonishing part about it is, besides that it works actually fine, is the full software stack of state observation, uh, state observation, and many other stuff, state observation, control loops, application layer, different sensor observation, stuff like that. It only took something around 84 megabytes from our computation or from our memory, and it took something up a processing load of something around 43%. And we will be presenting somehow, I will show you in the next slide, much more interesting results. But as you can see here, it goes from 0 to 100 and from 100 to 0 again. As we mentioned before, we can have the best feature of the new generation flight controllers in a global in different ways is is having kind of uh, is that you can get new is the scalability thing, where you can get much more observed states, or you can use lidars and cameras and integrate them to do your work. So simply here you can see that we have engaged the camera as our UCO markers to make somehow a map. And from this map, somehow we can observe the state or the pose estimation of the drone somehow in the 3D domain. By that, we can have something like a block of 2 by 2 meters. It can localize itself over it. And the astonishing part is just by making just few optimizations in our software stack, removing some debugging states, some debugging prints and stuff like that, it just made something around 45% of processing load, and the memory allocation is something around 121 megabytes. And somehow we're still guarding it from hovering, because we are making pose estimation, not position hold. So the next step is simply position hold, to use the pose to be able to hold itself at 0, 0, and then goes and hover in this 2 by 2 meter square. About the future work, we are expected to, first of all, invest more time in more simulations, invest more time in engaging AI over our software stack beside our kind of flight controller software stack. Having a TOF, a 3D Arduino cam, to have a kind of, to be able to make some mapping and some localization and stuff like that. And we think that we hope that we will do all of that over a single board somehow. And I hope it works out. Yeah. Some of the common question and answer QAs that we are somehow being asked. First question, does our software stack run over different hardware, or is it just limited with the with, for example, Raspberry Pi or something? The answer is no. Our software stack can run over a variety of hardware. Whatever embedded Linux target, it can run over it. Maybe if you will have to change, you will just have to change the hardware abstraction layer if you are required. Other than that, I think it can run over any embedded Linux hardware target. Second question that we are frequently asked. Today I have a classical plus setup. Why should I change my setup from the classical plus to a new generation or a new generation plus? Simply, the reason to the way of, or the need to change something like this, it totally depends on your needs. So if you have your software stack and your system is running super nice and super flawlessly over classical plus, you do not need to change to new generation. You will need to look into new generation when you are considering different tasks, such as, for example, if the drone agility is quite a crucial task for you, or a crucial parameter for you, then you need to consider the new generation plus plus or the new generation. If your if you are required to somehow having passing through an unsafe something that requires a lot of safety or a lot of sensor what's called sensor suit to process a lot of sensor suit and to have a different layers of fusion that will affect your software stack. Then you will need to have a look into the new generation flight controller, and you need to consider it. Other than that, you are free to go. You are free to choose whatever suits you the best in a manner of what is most efficient for you and what is most cost and effort efficient for you. How do I know that this software stack that I am running is a new generation flight controller or a classical plus plus? Simply, the answer to this is the foundation of your software stack. If you have your software is all of it run over a different of subroutines over a microcontroller, then this is a classical one. If you have your somehow software stack is running over two different is divided into, some of it is running over different IPCs, different processes over a flight computer, and set of microcontrollers, and this is the classical plus plus. If you have your flight controller, your software stack is running over a flight computer, then it is a new generation flight controller. So simply, the foundation of the software stack is the thing that defines how things are working with you. What will happen if one of the software modules crashes, and what about redundancy? Simply, in the service-oriented architecture, it is better to or one of the advantages of service-oriented architecture, that you can have something called an administrative service, where in the administrative service is somehow look into sees the status of each process, and somehow if some process crashed, it tries to bring it up again. And what about redundancy? Service-oriented architecture or the new generation flight controller actually have an advantage where you can have multiple processes that are running different sensors or something like this. Or you can have a software redundancy rather than a hardware redundancy. And the final question that we are asked, or commonly asked, from where did we get the naming convention of our different architecture, of the different architectures? We are coming from the automotive background. And from this automotive background, somehow we learned from it how we name stuff. And that's how we named stuff here. So these are the common questions that we are asked. Questions?
Thanks a lot. It's pronounced Khalid then.
Yeah.
Or I'm so sorry
Khalid
for
in
mispronouncing
English.
it. I'm really bad with names.
No problem.
Also, I had to it was very nice to see the demos with this is a good exercise as well, right, for a lot of squats. So I had to. That's why I had to laugh a little bit, because I know that I have to do those at the sports school, and those can be quite tough. So you must have very good legs. So it's now time for some questions, right? So if anybody have questions or comments, I think now is the time to say. Ramon, I see that.
Anyone else from the group first? All right, so I guess I get started. How many people are working on this project?
On hands, three resources working in this project, but we have support from other two. One of them is a PhD from Montreal in aerospace and swarm robotics, but he is what's called a critique for our he is here just to challenge our ideas, to make sure that we are. He's always asking, why are you doing it this way? Why are you doing this way? Why did you take this approach? Why? So by that we are enhancing somehow to challenge our solutions. And the second one is from Sweden. He is a colleague from Sigma Sweden, Sigma Embedded. But the people who are working in this project are 3 headcounts.
Great. So this is not an academic project, right?
No. This is not an academic project. This is one of simply. Believe me, I'm not sure if you will believe me or not, but we did this by luck. So we didn't plan to do something like this. It was like we had requirements from a client that we thought we were working on a demonstration. It didn't move forward, but we figured out that in the demonstration somehow we did something that will be nice, and we studied the flight controller market, and we saw that there is a gap in this area to do it this way. And somehow, if you want to see other people who are doing the same thing that we have done, do you know Model AI? Model AI, I think, is one of the companies that has done this thing. So in Sigma, we said, why, let's not bury the good child that we have made, and let's proceed in it. So we proceeded in it for a couple of months, 3 months, and this is the output of the 3 months that we have worked in it.
Yeah, thank you. Yeah, to answer your question, yes, I know Model AI. They're a member of Drone Code.
Yeah, they're amazing. They are amazing. I think that soon we will. I hope that they are the thing that we are heading for. So we hope that our software stack will one day be able to do what they are doing.
You do know they're using PX4, right?
I know. But as I'm telling you, in our software stack, we do not. Before I say my opinion is, they are the market leaders right now in their solution. But we do not need a dedicated DSP to run our software stack over the board. We somehow need an SoC that is as humble as Raspberry Pi Zero, for example. Our software stack runs over Raspberry Pi Zero. Besides, of course, most of our tests, or the tests that we have presented in front of you, is done over Raspberry Pi 4. But our software stack is as optimized, as efficient as it can run over Raspberry Pi Zero. So we do not need. Yeah.
Thank you. Not sorry to cut you off. I didn't mean to that.
Pardon me?
I didn't mean to cut you off. Sorry. Please continue.
No. Thank you, Ramon. No.
Okay. One last question before I start. We have a lot of other questions in the chat, but let me, before I go on. So you have 3 full-time team members and then 2 part-time. And how many flight hours does this flight stack have already?
Flight hours?
In actual physical vehicles.
That's a tricky question. Up till now, we have. Let me show you. So, can I stand up and get the drone for you? You have seen the first drone. So we have 2 drones. We are trying to put our software stack over it. First drone is
I guess email will be fine. You don't need to be exact.
Yeah. The flight hours, it is just the tests that we had. Just the few tests that we have here. So, for example, if you say we make tests for half of our day, of our working day, we're making tests over it. So we are talking about 4 hours multiplied by, for example, 2 months when we started flying. So 160 hours. That's the maximum. I think that's something plus or minus 160 hours. But of course, in laboratory flying tests, no more, no less. So we didn't go outside and stuff like that. So our added value, Ramon, here is we think that we will add a huge added value in the GPS denied environments. So we do not need for now to go outside. All what we need now is to prove how efficient is our software stack in GPS denied environments. And simply, this is our way to go somehow. And the first drone is a drone that you saw in the demos. The second drone is, I'm not sure if you can see it or not. So this is my hand compared to it. Can you see it? Let me remove the background a little bit. I do not recall how to remove the background. So can you see the drone?
Yes.
Yeah, so this is the second drone that we are trying to put our, I'm not sure, pardon me for that. It is as small as the Crazy Fly, but of course not as small, but it will just, we are planning that this small drone will have Raspberry Pi Zero that will be able to somehow do all of this stuff in addition to some AI and some stuff like that.
All right, now my really last question, is this open source?
Up till now, no, but we do not mind to make it an open source.
All right, sounds good. Now, maybe can I read questions from the chat?
Yeah, go ahead.
If I would add something, if you, we are not as good as you guys in making things open source. So if you have recommendations, share it with us. We will consider it in our meetings and we will discuss it in house, within the line managers that you can see here in front of you. So these are the 3 line managers of this software product or software stack. Just if you have recommendations, if you have a way to an advice or something like this, just bring it up and we will see how things will work out. We will discuss it in-house.
All right, thank you. I have a question from Bonalo on the chat. And the question is, are you running each layer as multiple processes in a single CPU? What is the overhead of allowing clients to subscribe at different frequency rates?
So we are running each layer as a multiple processes in multiple CPUs, not in a single CPU. So we are utilizing all the CPUs, not in one CPU, but in all of the CPUs that are over the embedded Linux. What are the overhead allowing clients and subscribers for different frequency rates? 0. Somehow there is a trick in the design itself. We're simply you need to identify what are the periodic tasks, what are the periodic servers, and what are the non-periodic servers that are somehow guarding a certain resource. And when you somehow identify things like this, it just works. For us, we didn't have limitations. And if I would go back a little bit, pardon me for that. So this is the most costly process. You can see here we are having 120 thread, 45 tasks. Average load is 1.95, and somehow it is still 45% in the processing load, and we can go lower than that. If we made more optimizations, and we can do more optimizations, because in the demo that you can see here in front of you, somehow we want to stress test our software stack, because we want to see how it works, in an efficient way. So there are many things here that are not optimized, so we can go lower than 45% in such case. And as you can see here, it can make an estimate for the pose itself in manner of centimeters somehow. So I hope this answers your question. And yep.
All right, and then there's a good follow-up by Alexis. Do you do some sort of profiling in your system?
Again, please.
Do you do some sort of profiling in your system?
Up till now, the only profiling is the only thing that we did is to measure how the edge top that we measured through kind of the load over the memory and what's called memory and processing power through each top. But there are many different ways that somehow, or many different things that we need to do, but we know it is just a 3 months or 3.5 months long project. We started it, by the way, Kim, when I sent you the first email. By that, it was like we had only one server. And somehow, up till now, we have built all of these servers somehow to make things work.
All right. Yeah.
Yep.
Yeah, Mayank, you have one more question. So let's do the last one, and then we'll close for today.
Yeah. Khalid, what OS are you guys using? Is it like default Raspbian? Have you modified?
We are using Ubuntu Server 20.04.
But are you modifying it with the RT preempt patch in the kernel? Like, how do you have real-time or deadline guarantees in your OS?
We have made zero modifications in this manner. So we used ROS as it is.
ROS, sure, but like you're also running a flight controller in the OS, right? So there's no real-time guarantees on your flight controller is also
we are using
right?
the real-time guarantees that we have is the guarantees that is provided by ROS2. So this is the things that we are using for now.
Okay. Thank you.
Yep.
All right, I'm going to close it off for now. So thanks, Khalid, for giving this presentation. I'll just
Thank you, Kim. It was an honor for me to be part of this.
Glad to hear. I'll just reshare my slides just for some final announcements. If there's any other questions, please ask them like as an email or in the discourse thread where the meeting was announced. Let me just try to find the presentation again. I'll just keep it very short. Yeah, so yeah, so like I said before, we're going to have a summer break, which means there's not going to be any meetings in July and August. Also because at least the next one, both me and Ramon will be able to host. We don't have any guest presenters. So let's just take a break. But of course, keep on chatting on Discord, start Discourse threads. And of course, you can also use this meeting link if you would like to just meet up with each other if you're working on, I don't know, some Aerostack 2 prom and you just want to meet people, just like, you know, go for it. If you want it recorded, you do have to let me know, then I can join to record it for you or make your own Google Meet. Yeah, so the GitHub organization for this working group is github.com/Ariel. Also, Ariel Robotic Landscape. I've been telling that a couple of times. Keep adding stuff during the summer. Hopefully, that's not going to be on a break. Yeah, and that's it. And also, yet again, if you would like to join the Robotics Developer Day, just send me a message or an email, and then yeah, I can give you a discount code for you. All right.
Thank you.
Thanks a lot, everybody, for joining. Thanks, Khalid, again for giving this nice talk. And see you then technically, officially in September again.
Bye-bye.
Bye-bye.
Thank you, Kim. Thank you, everyone. See you in a few weeks. Goodbye.
Bye-bye. Bye-bye.
Thank you. Bye-bye.
Thank you. Bye.